My name is Topher, and that's Christopher Olson, or Topher, not Topher Olson, thanks. I'm going to talk about Treode, which is yet another database, although this one has some unique features. Otherwise, I would not have bothered to build it. Treode supports distributed transactions, and very few open source databases do that. And Treode gives you very clear guidance on how to integrate eventually consistent components, like caches, with the transactional mechanism. And it is the only database that does that. So I'm going to talk a little bit about what that means and why it matters. But ultimately, I'm here tonight to get you excited about this and encourage you to help out. Treode is an open source project that's been largely the result of my own efforts. Recently, a couple of folks have jumped in to help me out. They're here in the front row this evening. And that's been a relief, but there's still more work to be done. So the site dbengines.com lists over 200 databases to choose from. Why do we need another? Well, if you want distributed transactions. And why would you want that? So when we have one database, we have a very simple situation. We have one source of truth. However, the machine that is running this database might crash, and then our whole site could go offline. Well, that's no problem. We just replicate it. Now we have it running on multiple machines, so that if one machine crashes, we have another machine to pick up the load, and our database can stay online. There's another issue. The size of our data set, or the load from our users, might outstrip the capacity of a single machine. That's no issue. We just divide the data into pieces, and then we can scale with load and data size. Ideally, we want a database that is both reliable and scalable. We want it to be both replicated and sharded. In all of these cases, we've built a distributed system. Our original problem was that a machine might crash. Well, now we have multiple machines that might crash. Furthermore, the network that is connecting them might pose troubles. These are hazards that distributed systems must be prepared for, because it's not a matter of if they happen, it's when they happen. So there's already a number of databases that are reliable and scalable, and they've served some very lucrative websites quite well. So if those are already around, why do we need another? Well, the existing databases solve the hazards posed by distributed systems using techniques that are eventually consistent. And that works great for some applications, but it does not work for other applications at all. I'm sure that some of you in this room are familiar with eventually consistent databases, transactions, and distributed systems. But I'm assuming that most of you in this room do not eat, sleep, and breathe this stuff. So I'm going to spend a little time talking about the hazards that distributed systems pose and how eventually consistent databases solve them. And then I'm going to compare that to how transactional databases solve them. In the end, you'll see that the two databases are appropriate for different kinds of applications. So what can go wrong when we replicate? Well, let's imagine that we have a shopper placing items in their shopping cart. When we have one database, we have one view of what's in that shopping cart. When we have two databases, we run the risk that the replicas diverge. So here we have a science fiction geek buying themselves some toys. Our shopper adds the lightsaber to their shopping cart. And the message to do this reaches both replicas. So far, so good. Then our shopper adds a model of a tricorder to the shopping cart. And the message to do this reaches only the first replica. Finally, our shopper adds a model of a Cylon Raider to the shopping cart. And the message to do this reaches only the second replica. So now our two databases disagree on the contents of the shopping cart. What are we to do? Well, we can treat this with branches, much like we would handle files in source control. And we can leave it to some reader who eventually discovers the divergent branches, and that reader can merge those branches. This is how it's done with Amazon's DynamoDB. This is how it's done in CouchDB. And this is one of the options in Riak. When we're adding items, everything looks fine. but when we delete, we run into trouble. So here, our shopper has accidentally added the book Star Trek Memories to their shopping cart. And the message to do that reached the first replica. Then our shopper realizes their mistake and deletes the book from the shopping cart. That message makes it only to the second replica. So now one says add the book and the other says delete. How do we reconcile this? In this case, Amazon chose to favor adds over deletes. Now, at the time they made this decision, mostly they were sending books. And if they accidentally sent you a book you did not want, it was not too onerous for you to take the book back to the post office and mail it back for full refund. However, what if we're selling this to a construction contractor? This is expensive to ship, and it is expensive to ship back. So we have made an expensive mistake. Well, let's just turn this around. Let's favor deletes over adds. In that case, we risk not shipping it when it was wanted. So it doesn't show up when it's expected. Construction crew sits idle. The schedule is delayed. The contractor incurs penalties with their customer. We've made a different expensive mistake. Merging is ad hoc. Here, for example, we have two users change this text at about the same time. And we all know that this text is supposed to contain every letter of the alphabet. Only one of the three sentences on the screen actually does. Clearly, we are not going to program that in as a general heuristic for merging text. So let's try a different approach. Let's treat our shopping cart as a set. And whenever two replicas diverge, we'll reconcile the problem by doing set union. This is known as the convergent replicated data type. And it's convenient because our reconciliation is no longer ad hoc. And the storage system can provide for us some common abstract data types. And the storage system can take care of the reconciliation transparently. This is one of the options. This is another one of the options available in React. However, it's just another way of saying that we favor adds over deletes. Yes?
Is it easy to timestamp the operations?
Is it easy to timestamp the operations? You're getting ahead of me. We will get there. So what would a transactional database do? Well, it would await acknowledgement from a simple majority of the replicas. That way, it gets the latest answer from at least one of them, while it can still tolerate an outage of a minority of them. Our eventually consistent database needed to await acknowledgement from only one replica, so it can tolerate an outage of more replicas. In other words, we have traded availability for consistency. What can go wrong with sharding? A database for movies provides an excellent example. Here we have a table of movies, and each movie is a complete object. It contains the full cast of that movie. And we have a table of actors, and again, each actor is a complete object. It contains the full list of roles that actor has played. These tables are redundant, but that's okay. We figured that reads outnumber writes. So we do this to favor the reads at the expense of an occasional write. Our writes need to update two objects. We need both updates to go through, or a database may become semantically inconsistent. We can write a program that makes one update and then the next. But what if the program crashes between those two operations? HBase and Cassandra give us a tool to bind multiple updates into an atomic unit. That is, they complete all or nothing. But that tool is only available if the objects happen to fall on the same shard. If we use a database like MySQL or Postgres in a sharded way, we have that same capability. We can bind multiple updates into an atomic unit if they fall on the same shard. The problem is that we cannot always structure our data to satisfy that requirement. And here we have an actor on one shard and the movie on the other shard. We run the risk that the update makes it to one shard, not the other, and leaves our database in a semantically inconsistent state. So what would a transactional database do? Well, it would coordinate the write in two phases. In the first phase, it asks each shard that's involved, can you do this? And in the second phase, it then tells each shard to commit or abort. When a shard acknowledges the first phase, it is obliged to commit or abort as the coordinator says. Even if that shard should crash, it has to restart, recover its state, recognize that it was in the middle of a transaction, and return to the coordinator to find out if it should commit or abort. Our eventually consistent database needed one round trip, and here we need two, which adds latency. So we've traded latency for consistency. The atomic multi-row write gives us a tool to handle these situations. Here are a couple representative examples of transactions, and I want to emphasize representative. Banks and merchants are free to implement their business processes in any number of ways, but these illustrate some of the problems that can arise. The bank transfer is the quintessential example of a transaction. We want to debit the source account and credit the receiving account. We want to do both of those things, not just one of them, or somebody will lose money and be unhappy. Implementing a transaction on a single node is relatively easy. To implement it in a distributed way is a little more difficult. Treode uses a distributed protocol that can coordinate multiple replicas of multiple shards to implement an atomic multi-row write. So the protocol is a little tricky. The client is not on the hook to implement the protocol itself. It contacts an agent to run that protocol for it. And that agent is available on every server in the storage system. So the client can contact any host in the cluster and ask it to execute a write on its behalf. Any presentation about distributed systems is required to mention the CAP theorem. It's just a tacit rule. When we build a distributed system, there are three properties we would like from it. We would like it to tolerate network partitions. We would like it to be available 24/7. And we would like it to give us consistent answers. The CAP theorem says that we can have two of these. Eventually consistent databases and transactional databases differ in which two they choose to provide. To choose between the two, you need to consider the requirements of your application. So for example, if Google or Facebook was slow or unavailable, they would lose advertising dollars. On the other hand, if Google gives you search results that are a few minutes stale, you probably won't even notice. And if Facebook interleaves two timelines differently for two different viewers, that probably doesn't matter. So for them, eventually consistent databases make perfect sense. But remember our supplier of that very large item to construction contractors from earlier. For someone like that to act on stale or inconsistent data, they risk lots of money. They might prefer to spend a second on a transaction, and they might prefer to delay their operations if the database is unavailable. So for them, a transactional database may make more sense. I want to take a quick digression about the word consistency. Within the domain of storage systems, we use the word in a variety of ways. We do that to keep the lay people at bay. So on the one hand, we might use the word consistent for the notion of semantic consistency. Remember earlier when we wanted to add Harrison Ford to The Empire Strikes Back and add The Empire Strikes Back to Harrison Ford. If we did not do both of those things, our database would be semantically inconsistent. Other times we use the word consistent to mean something along the lines of the replicas match, they agree. Throughout the presentation, I will try to be clear about which notion of consistency I mean. So if you have some big bucks, you can get transactions in a scalable and reliable database by purchasing Oracle or DB2 or SQL Server. If you'd prefer a cheaper open source solution, well then you can have transactions, or you can have scalability and reliability, but you can't get them all together, until recently. TreodeDB provides all of these things in one package, and that is why we need another database. So now we understand why, let's look at how we use this thing. I'm going to show you something known as the Conditional Batch write. Treode is a key value store, which is a fancy way of saying it's an overgrown hash table. As such, its API is dead simple. It's read, write, and scan. Only there's a catch. There's these timestamps running through. So let's look at what that means for read and write. We'll come back to scan in a little bit. In a traditional database, we would wrap reads and writes between begin and commit. And the database would gradually lock data as a transaction read and wrote it. And it would hold those locks until the end of the transaction. Treode takes an optimistic approach. This means that as the transaction reads the data, the database does not lock it. And as the transaction writes the data, it writes only its own local view. When the transaction is ready to commit, it binds all of its reads and writes into a unit and sends the entire batch to the database. The database is locking data only during the short duration that it's applying this batch. And it applies the batch only if none of the data has changed in the meantime. It's possible that a concurrent transaction has changed some of that data in the meantime, in which case the first transaction will be notified that it acted on stale data, and it can restart and retry its operation. Now, these retries may sound like wasted effort. They may sound like a cost. It turns out that the implementation of the locking mechanism for the traditional approach can be so costly that on balance, the retries represent a net savings. So we've seen the read and write API, and we've seen the retry loop. Let's bring this together. With Treode, we choose a time to read as of. Generally, we read as of now, though we could read as of some time in the past. The database returns to us the value for that key as of, that is, that was set on or before that time, as well as it returns the timestamp that that value was written. Read also arranges under the covers that any subsequent writer will use a timestamp greater than the one we had used for reading. So in a distributed system, the clocks on our machines are going to be slightly different. We're going to have clock skew across our cluster. This has been no end of trouble in some distributed systems. The mechanism you see here, where read arranges that subsequent writers will use a greater timestamp, is a form of Lamport clock, and it addresses the problems posed by clock skew. When we write our modified value, we include a timestamp as a condition. The write will succeed only if none of the data that's being written has changed since that timestamp. Here we're using the same timestamp that we used for read for our condition. We could also have used the timestamp from the value as our condition. In fact, we can use any timestamp between those two. This inequality is important, and it's going to pop up later. So let's look at a concrete example. This one where we had two users try to change the text at about the same time. And as we look at it, we'll also see how it manifests in HTTP. So both of our users ask for the current value. They get back the text, and they get back the time that it had been written. The first user then writes their update, and they include as a condition this timestamp from the original value. Nobody has changed the value since then, so this update succeeds. And the first transaction gets back the timestamp on the new value. Our second user also writes back their new value, and they also use the timestamp from the original value as a condition. This time, somebody has changed the value, and so our second user is notified that their condition failed. What about this example? Yes?
So you're only doing row-level locking, you're not going down to the block-level storage?
It is row-level. Yeah, the question was, is it row-level locking or block-level?
Yeah.
It is row-level locking. Yeah.
So what will happen if the transaction is reading record A and writing record B?
Ah.
So you take the timestamp.
Yes. So the question is, what if a transaction has a read dependency and it does not write a piece of data? In Treode, there is an operation to indicate that you're interested in an item having not changed, even though you have no intention of writing it. So you can introduce read dependencies into the transaction. So what about this example? Yes, question?
Will you eventually characterize the kind of guarantee that Treode provides? Is it, for instance, serializability? Is it snapshot isolation? What?
It is serializable snapshot isolation.
Never heard that one before.
Okay, SSI? So let's look at this example where we needed to update multiple items at a time. Both read and write work in batches. So we can ask for both the movie and the actor, get back their current values and their timestamps that they were written, and then we can write the updated values as a batch. And the batch will complete as an atomic unit, that is, all or nothing. So this conditional batch write is a handy tool, but it is just that. It is a tool. It is not magic pixie dust. We must use the tool wisely. In particular, we need to avoid hotspots, so avoid things like global counters. And we need to keep the write batches small. 2 to 10, what does small mean? That's all relative. 2 to 10 rows, that should be okay. 100 rows, you're probably okay. 1,000 rows is starting to push it. And the entire database as a single write batch, definitely not. These guidelines are as true for Treode as they are for traditional databases. In fact, these guidelines are true for concurrent programming in general. So let's look at how caching interact with read and write. When we talk about caching, we need to ask ourselves a number of questions. The first question, at least 2 of them are here. Are we caching the rows from the database? Well, probably not, and I'll show you why in a moment. And are we caching those on the database server? Well, certainly not. So in the original movie example, we considered the movie object complete, and we considered the actor object complete. But here we're going to look at an alternate way to model that data. We're going to set up 3 tables. The movies table is going to have just the title. The actors table is going to have just the name. And the roles table will have the character. So when we want to build a complete object for a movie, we need to get the title from the movies table, all the characters from the roles table, and then all the actors' names that played those characters from the actors table. We can finally assemble all of that into the result that we really want. It is that composite object that we would cache, not the individual rows. When we build a composite object like this, we can also compute a timestamp for it. It is simply the maximum of the timestamps on all the rows that went into building it. And we want to cache it as close to the client as we can. That may mean on the client itself, or it may mean at the edge on a server close to the client. If worse comes to worse, we cache it in the middleware. If we manage these caches carefully, we can use them to optimistically execute a write back to the database. So in our cache, we'll certainly map the keys to the values, but we'll also track the timestamp on the value, as well as the timestamp that we had used to read the value. If at any point we find a value that is newer than when we had read some other one, we can suspect that our cache is semantically inconsistent. So for example, here we see that Empire Strikes Back is newer than when we had read Harrison Ford. So we can guess that our cache has the version of Empire Strikes Back with Harrison Ford in it. And we can guess that our cache has the version of Harrison Ford without the Empire Strikes Back in his roles. Furthermore, we can see exactly which values we need to refresh. When we refresh those values, we find that every item we have read, we've read it sometime after all the items have been written. In this case, we know that our cache is a semantically consistent snapshot of the source database. Now, it may be a stale snapshot. That is, as a replica, it may be inconsistent. But semantically, it is consistent. We can use the data from this cache to execute an optimistic write back to the database without rereading from the database. And when we need a timestamp for the condition on that write. And down there at the bottom, you see that inequality from before. We can use any timestamp in that range as our condition when we execute the write. So some databases use a technique called optimistic concurrency control in their implementation. And some databases use a technique called multi-version concurrency control in their implementation. And then they hide those techniques, they hide those features behind a traditional begin-commit interface. Treode exposes them through its API in a clean way. And by doing so, we allow caches to be integrated into the transactional mechanism. Databases that use these techniques in their implementation do so for reasons of concurrency and distributed programming. They hide those techniques behind a traditional begin-commit interface because of legacy. Treode exposes them for reasons of concurrent and distributed programming. Yes?
So what you're talking about is effectively a way of doing cache coherency. What you're also considering is that your time synchronization between all nodes is within a certain delta. So are you actually doing that time synchronization internally within Treo, or how are you doing that?
The way we deal with the clock skew is because read sets up a Lamport clock that ensures a subsequent write will use a greater timestamp. So we use so the question was what happens with clock skew in the cluster? And this is how we deal with that. We do use the system clock as a guide, but it is just a guide. By using it as a guide, the write timestamps actually have some meaning to the user, but by using the Lamport clocks as the final authority, we resolve the problems that you're hinting at. So that takes care of read and write. Let's return to scan. Scan has 4 parameters. The first 2 are fairly self-explanatory. What table are we scanning? Where within that table are we beginning our scan? The other 2 parameters need a little more explanation. So Treode is a versioned database. That means that you can scan it over a window of time. For example, you can ask for all the changes in the past 5 seconds, or you can ask for the latest changes in the past 5 seconds. The difference between those 2 is consider that one row was updated multiple times in that period. Do you want to see all of those updates, or do you just want to see the most recent one? So either of these options would be great for streaming analytics. Or we might ask for all of the changes over a 24-hour period. That'd be great for daily analytics. And we might just scan the whole database. If our database is truly petabytes in size, we are not going to scan it from one thread in one process on one machine. We're going to scan it with parallel workers. The slice parameter allows us to set up parallel scanners that correspond to the shards in the database. So here we have 8 scanners, each working on one shard. Now maybe the scanners don't have that much work to do. So we could have 4 scanners, each merging 2 shards, or 2 merging 4 shards. We could even go the other direction. So for example, maybe our scanners have a significant amount of processing to do on each row. We could set up 16 scanners, each takes half a shard. Which half depends on how the keys hash. These slices correspond directly to partitions in Spark's resilient distributed data set. So Treode can serve as the source repository for an analytics framework that's based on Spark. And Spark has its own notion of caching. You can ask Spark to persist intermediate results. And speaking of caching, scan lets us do something interesting with the caches from before. So earlier, I had tacitly assumed that when data was not in a cache, we would react by reading it at that time. With scan, we could actually proactively refresh those caches in advance of a read. Scan serves another important purpose. Let's consider sophisticated search indexes that support full text or faceted search. The operations that update these indexes break the rules for transactions. They create hotspots and they write large batches. Updating these indexes as part of a transaction is a bad idea. Not that that stopped people from trying, but you shouldn't do it. What you can do is bundle all the changes over a recent period into one mass update. So for example, we can use scan to update our search and indexes every 5 seconds. This way, our indexes are reasonably current, but without adversely affecting our transactional operations. Let's see what Treode looks like in a larger picture. Yes?
So the API to scan, the 4 parameters, it seems like the first 3 parameters have to do ipso facto with the data. And it seems like the 4th parameter is an implementation detail that it would be nice if the system decided what the optimal splitting of the logical scan operation would be. Or am I wrong about that?
You raise a good point. So the observation was that, I'm not going to flip all the way back, that the first 3 parameters are really related to the data and functionality that you might want in an application. And the 4th parameter looks more like an implementation detail that you would like the system to take care of. And the answer is, yes, Spark takes care of it.
Okay.
So let's look at Treode in a larger context. So we have Treode running on 5 replicas. 1 in San Francisco, 1 in New York, 1 in London, 1 in Amsterdam, and 1 in Singapore. And caching is not a part of this deployment. So as I click from movie to actor to movie, you can sense a little latency. And that's the latency from forming a quorum around the world. And we could even add an actor to a movie. And we'll say that Luke Skywalker starred in this movie, whatever it was. And again, you can sense a little latency. A lot of latency. So the point of this demo, it's not really to show you that Treode works. I mean, you can see it works, but that's not really the point. The point of this demo was to give you a sense of the latency when the replicas are located around the world. And as long as a majority of the data centers are online, our database is available. So we could have an earthquake here in San Francisco that wipes out this data center and sends a wave of energy through the Pacific that creates a tsunami wiping out the Pacific Islands, Singapore, and our data center there. And our database would still be online. I had mentioned that when choosing transactions, we gave up availability for the consistency. Well, you can see we didn't really give up that much. I'd also mentioned when choosing transactions that we traded latency for the consistency. And you can see, you can feel firsthand the latency here. This may be acceptable for some applications, especially applications that want that disaster resilience. It may not be acceptable for other applications. In that case, they could locate all of their replicas in one data center. They no longer have the disaster resilience, but they do still tolerate the outages of individual machines. And they would reduce their latency by about 3 orders of magnitude. Not many databases talk about being geo-replicated, at least not in a way that's integrated with the transactions. If you look at, say, Oracle or Postgres, you can do geo-replication, but it's in an asynchronous way. And there's a master failover process that's rather messy, and you may lose some updates when that happens. And there's a reason why most databases don't really discuss geo-replication. If you take kind of a naive approach, each individual read and each individual write that the transaction makes could incur that latency, and that would add up. But with the conditional batch write and the ability to integrate caches, we can most of our reads will come from the cache, and our writes will go to the local view. So we incur the latency only on a cache miss, and we incur the latency only at the commit, at the batch write. The conditional batch write gives us a way to tame this latency and actually make georeplication something we might consider. Let's return to our shopper. In fact, let's expand on this a little bit. Let's say that our application is a marketplace, because that's all the rage right now, to bring together shoppers and merchants. As our shopper browses the catalog, flipping from item to item, that latency you saw would be annoying, and our shopper would run off to another site. We can handle that problem. We can serve the product catalog through a cache. That cache will be eventually consistent. We can refresh it either reactively as the user's browsing or proactively using scan. Our merchants, perhaps they're companies of, say, 30 people. That's just enough that 2 or 3 people are responsible for maintaining the product catalog. And that's just enough that they may trip on each other's toes now and then. So they'll want to use the product catalog in a transactional way. They're going to incur that latency, but they aren't updating it all the time, so it probably will not annoy them too much. And for reasons we discussed earlier, our shoppers will want to use their shopping cart in a transactional way. Again, they aren't updating it frequently, so that latency may not be too much of a bother. When I discussed eventual consistency versus transactions, I had suggested that we need to consider the application's requirements and make the decision for the application as a whole. But you see here, we can actually be more refined than that. Are we making the decision based on the data? Well, no. We have the product catalog that is being used in an eventually consistent way by our shopper and in a transactional way by our merchants. So are we making the decision based on the user? Well, no. We have a user who's using one piece of data in an eventually consistent way and another piece of data in a transactional way. We are making this decision use case by use case. So we have eventual consistency and transactions working together. This diagram is representative of data architectures in companies today. And there's a couple concepts hiding in here. SQL gives us transactions. MongoDB, CouchDB, they're very scalable, reliable. Things like Lucene, Sphinx, Solr give us sophisticated search. Kafka is really great for streaming analytics. A full-fledged application generally has features that require all of these things, and so it generally has all of these databases. This is known as polyglot persistence. Our business analysts, they want their weekly and their daily reports, and they also want up-to-the-minute statistics. So they want both batch analytics and streaming analytics. Between the user and the databases, there is a set of cooperating processes. I've blithely drawn them as a single box here called the coordinator, but it's a set of cooperating processes that execute requests against all the databases. So any given request from the client could potentially touch multiple databases. What exactly this set of processes looks like depends on the databases on the back end and the features of the application. We have an architecture that is tightly coupled. With the conditional batch write and with the ability to scan over windows of time, we have another option. So here we have a router, and the sole job of the router is to take a request and direct it at one backend. The router does not coordinate multiple backends. Our transactional requests go through the middleware to the database and back. Requests for things like search go just to that service and back. Search refreshes itself periodically using scan, and Apache Spark serves both the streaming and batch analytics. Now we have a much more flexible system. For example, if we discover our search instances are being overloaded, it's easy for us here to add new instances. And it's easy for us to locate those instances closer to the user. And with Spark, as our business analysts increase and decrease their demands on the analytics framework, it's much easier for us to increase and decrease the machine pool that's serving Spark. We have a loosely coupled system. So by now, I hope you're wondering how Treode is implemented. And actually, I know you are because some of you have asked me some questions. We've seen a few of the implementation details. We've seen Lamport clocks, optimistic concurrency control, two-phase commit, and the quorums. I only have an hour to talk tonight, so I won't get to go into much detail on this. You'll have to invite me back for a second lecture, and that's fine. I love talking about this stuff. But I do want to say this before we close. In a traditional database with full ANSI SQL, you're allowed to make a statement like that at the top, which updates an entire table within a transaction. This is a bad idea. You should keep your updates small. But SQL allows it, and SQL databases need to be able to support it. So they need a lock manager that can work very quickly and efficiently for well-behaved applications that update only small numbers of rows. And yet, they need that lock manager to be able to adapt to these broken situations where the application locks large portions of the database. Implementing a lock manager like that is hard, even with a single node. It's wicked hard when you have a distributed system. Treode's write batch discourages this bad behavior. The client has to build an array or a linked list of the items it wants to write, and then it has to serialize those items and send them over the wire to the database. If the client is beginning to update large portions of the database, the client is going to become aware of that. With the bad behaviors discouraged, we can make a lot of simplifying assumptions in the implementation, so significant that actually the implementation becomes tractable. So where are we at? Well, you've seen that it works. If you use MongoDB or MySQL or any of these, you can install a package and have a server running in a few minutes. You might expect that with Treode too. It would be a completely reasonable assumption, but it would be wrong. Treode is packaged as an embedded database, and that means it is a library for programming your own servers of a storage network. It's in Scala specifically. When you write that service layer, you need to make decisions about what is the data model and how are you going to represent the data and how are you going to represent reads and writes. Treode is structured as an embedded database to give you the flexibility to make these decisions as you see fit. And although it's very flexible, it's not very usable. So we're working on a service interface that exposes a RESTful JSON store. So we're at version 2, version 0.2. We have the embedded Scala API. We have read, write, and scan as I've explained them. We have the transactional mechanism as I've explained them. We also support changing servers in a live cell, and we support changing disks on a live server. What we need is the RESTful JSON API as I explained, and we need clients in various languages to go with that. We need stress and performance testing, and we need documentation. The documentation there is something I wrote, and I understand it. So what can you do? Well, just starring our repository would be cool. That would give us a little encouragement. Spread the word. Ask your friends about this, and ask them, hey, do you think this guy's completely off his rocker? And when they say yes, you can then shoot back, great, but what about the technology? We welcome casual contributions, and if you're interested in doing something more serious, come see me. Ultimately, though, we're looking for a pilot application, and perhaps you know a use case. Treode is a database with a unique combination of features you will not find elsewhere. It is distributed, so it's scalable and reliable. It supports conditional batch writes, which makes it easier to write applications. It shows you how to integrate eventually consistent components like caches and search indexes. And it's open source, so the price is right. Well, I thank you for listening to me drone on for 50 minutes. Now I'll turn the floor over to you for your questions. Yes?
So you had a previous slide, OMVCC transactions, optimistic multi-version concurrency control?
Yes.
So write skew is possible.
The Lamport clock.
Do you know what write skew is, the write skew anomaly?
Oh, right skew. Okay, you're talking about something else. No.
Right, so it's a source of astonishment for programmers who are expecting serialized semantics of a transaction. Optimistic multi-version concurrency control admits the possibility of a certain anomaly that cannot occur in genuinely serialized transactions.
Oh, okay.
Right? So we can take the details offline.
Yeah, and I think you're getting at the same kind of question that maybe this fellow was.
So,
Yeah.
I mean, that's fine. I mean, many databases by default will give you multi-version concurrency control, and the application developer is simply expected to know that anomalies like write skew are possible.
Okay.
Reckon with that possibility. So I think that answers my question.
Cool. Yes.
Did you consider other languages than Scala? I mean, actually, Scala is a good choice. Scala gets kind of overused for something, popularity, but here it's good.
Right?
But there are others, and what's your feeling about some of them?
Yeah.
Some of the others.
So the question was essentially why Scala?
And what else did you
Yeah.
consider?
So when I decided to write this in Scala, I could look at Cassandra on HBase and see that, all right, Java is obviously not an impediment to having a successful database. And I could say, and I could realize Java has garbage collection, which when I'm prototyping a system, that's going to be really helpful. I chose Scala because I wanted to learn it, and it was compiled to the JVM, and it had the garbage collection, and it took out a lot of the boilerplate in Java. And I figured it's not a bad place to start for prototyping. Having said that, I'm not married to Scala. If it turns out that Scala is a source of performance problems that we cannot resolve, there's a very natural migration path into Java. And if it turns out that Java is a source of problems that we cannot resolve, there's a workable migration path from Java into C or C++. So I think that this is just a starting point. Yes?
So on an individual, so let me ask you first, does Treode scale down to a single node database?
Yes.
Okay, so in that case where you have a single machine, a single storage device, can you tell us about the implementation of durable transactions there?
Sure. Okay, so the question was, when it's scaled down to a single node, what is the deal with how are the durable transactions? There's a write log, and it's log structured merge trees. Does that answer your question? Great. Other questions? Yes, in the back.
Can you explain how you create shards and also some about the data modeling?
The data model. Okay, so there's two questions there. So the first question was, how do we do shards? And we use hashing. So we take the table ID and the key and hash them. And we hash them into what I call the atlas, because the word map is already used quite prevalently in Scala. The atlas says which portion of the hash space goes to which replicas. And the system administrators get full control over this atlas. And when they want to change it, they just push in a new atlas, and Treode responds by saying, okay, I'm going to need to move data around. And it will update the atlas to reflect that it's moving data. And then when the data is done being moved, it will update the atlas to represent that the data is now in a new spot. Yes? Yeah.
Then when you have replicas, say geo-replicas, do they all have to have the same atlas?
Okay, so the question was, do all the geo-replicas need to have the same atlas? Yes, they do, and Treode takes care of that. So the admin just needs to push the atlas into any server, and that server takes care of coordinating to make sure that it's the only one doing an update to the atlas at the moment, and then it pushes the atlas out across the cluster in a gossip mechanism.
And then is that redistribution online, like in the background?
Yes, yes, the redistribution happens in the background. And there's a whole, actually this page kind of explains how it works. There's a whole mechanism where you can observe that the atlas is gradually being, that the new atlas is gradually being pushed out across the cluster. And then as soon as all of the nodes are aware that a new atlas is coming online, then they all switch to beginning to rebalance the data. And then as soon as that's done, an atlas goes out showing that the data is updated, that the data has been moved.
Okay, and then the data modeling, if I can ask that, do you have any sort of DDL or any sort of language support for like tables or any other?
Okay, so the question was, is there any kind of language support for any sort of modeling for a relational model or an RDF model? I have not provided anything like that. That's all work to be done. Yes?
I was wondering that what's the latency?
Right.
Transactional, and that's one question. Another question is, how could you ensure that there's no time differences between faraway data centers?
Right.
And since you work at Google, just want to mention that you know that F1, the Google database, they're using true time.
Yes.
And that's a very expensive device.
Yes.
So if this works, they could just save like 1,000 bucks for each
Yes.
two-time thing.
Okay, so there was a number of questions in there. The first question was latency. Okay, what is the latency? So actually, I was a little surprised at the latency that we witnessed this evening because I ran this morning and it's observable, but it wasn't quite as bad as we saw this evening. The latency that I've measured between these data centers has been anywhere between 100 milliseconds and 200 milliseconds. And if it's got to do, that's for round trip. So if it's got to do 2 round trips, you add that up. You're looking at transactional latency of 200 to 400 milliseconds. Maybe there's a lot of activity on the net tonight, and so we saw even longer latencies. If you bring all the replicas within a data center, your round trip times are sub-millisecond, and so you're looking at transaction times of 1 millisecond to 2 milliseconds.
And also, if you have a failure, and then probably you implement quorum or something like that.
Okay, so that's yet another question. Okay, so then his next set of questions was, about the clock skew. So the Lamport clocks address the clock skew. And his third question was, so in Google's spanner, they're using atomic clocks to reduce the clock skew across their data centers. And all that does is reduce, they call it true time, but there's still clock skew. It's just that the clock skew has been reduced significantly. And we don't worry about the clock skew because we're using the Lamport clocks. Or rather, I should say we do worry about the clock skew. We address it with the Lamport clocks. And your last question there was, I don't know, you had another question. Yes?
So what's the story about the secondary indexes? Are they local to a shard or they're global?
The secondary indexes? So if you, so the question was about secondary indexes. If you want secondary indexes, you would set up a second table, and you would, in your application, keep your primary table and your secondary table in sync. You would use the conditional batch rights to keep those in sync.
And then your transaction support makes them to be consistent.
Correct. The transactions allow you to keep your secondary indexes consistent with the primary table. Yes?
What kind of membership services do you use for all the shards across your cluster?
What kind of memory?
Membership service.
Oh, the question was about membership service. We don't have a membership service. We let the admins tell us what nodes they want in the cluster through this cluster map. Excuse me, through this atlas. In the Ceph file system, it's called the cluster map, and this idea comes from the Ceph file system. But as I mentioned, the word map is heavily used in Scala, so I called it the atlas here. Yes?
Just an observation, you can confirm this or not. This reminds me a lot of work that was done in the 90s between first implementations of Oracle OPS on True Cluster.
Okay, so the observation was that this reminds him of Oracle's work on the OPS cluster. I was there. Oracle did a distributed lock manager, and my lesson from that was don't do that. So I didn't. Say again?
Oracle did not do distributed lock.
They outsourced it.
No, they borrowed the code from us at Digital.
Oh, okay. So his claim is they borrowed the code from you at Digital. That may be true. I was working on a system called the Pyramid Mesh, and we outsourced it to Pyramid. They implemented a distributed lock manager for us. And as I mentioned, it was the cause of all the troubles. The project eventually was axed. And I don't think that's the only reason, but I definitely think that was a factor. Other questions? Yes?
My question again, so if there's a failure, for example, there's a conflict, just like you said, and then you add up latency big time from 200 or 400 up to...
Okay, so his observation is if there is a write conflict, you're adding latency. Yes, a successful transaction would incur that latency of 200 to 400 milliseconds. Each retry is going to occur it again, so it starts to add up.
So do you have any dependency on Spark, like Tachyon or anything? How do you do your buffer pool?
Right. The question was, do we have any dependency on Spark? The answer is no, we don't. The code base itself does not depend on Spark, though all it provides is scan, which is not really an end of itself. So you need something like Spark. You need some kind of analytics framework that the scan can feed into in order to make any sort of interesting analytics. And you were asking about a buffer pool. Can you be more, I mean, there's lots of buffer pools, so can you be more clear about?
The minimizing the I/O, right? So Spark has Tachyon now.
Oh, right, okay. So how do we minimize I/O? Yeah, we read the data off the disk, we deserialize it, and we cache the deserialized data. And that caches a whole LRU mechanism. Other questions? Yes?
So maybe it's just an observation, right? So if I look at this one, the thing like I kind of find new is what you call conditional batch write. Right?
Mm-hmm.
Since there are so many open source code, Cassandra, HBase over there, so could you just implement that feature on top of that one? Would it save you a ton of effort? So what happened over there? Like you need
Right.
to write everything, query plan everything from scratch to.
Okay, so there was a question and an observation. The question was, could Cassandra or could HBase implement this conditional batch write? Perhaps, though if they could, why haven't they done it already? Folks have asked a similar question about MongoDB. Could you do something like this in MongoDB? Frankly, MongoDB took a very long time just to get rid of the global write lock, so I'm not sure they could do this. Your observation was that we need to re-implement a query mechanism with this. Well, no, we leverage the query mechanism that comes available in Spark or that comes available in H2O or that comes available in any of these analytics packages that you can run on top of arbitrary source repositories.
So basically you're saying there's no way you can implement that part on top of Cassandra or HBase?
I will not claim that you can't implement conditional batch write on top of those. It's just I'm wondering, it's a very useful feature, so, if they could have done it, wouldn't they have done it by now? They may have technical problems implementing it, or they may just have sort of ideological, philosophical problems against implementing it. I'm not going to claim it's not possible. I haven't looked at their code base that carefully and thought about it that hard. Yes?
This is a comment just because we're talking about conditional batch write. I mean, to me, the pattern is very familiar just using SQL databases of, I read some data from the database. The minute I did, it might be out of date. I'm going to do a write based, and I'm going to throw things in the where clause based, not just on the things I want to update, but the previous value to make sure the row hasn't changed, right? And I'm wondering if one of the things in conditional batch write is that there's domain knowledge about what to do when you get a conflict and a race conditioning of two people writing the same data.
Okay, so the question was, with the conditional batch write, Is there domain knowledge in responding to the right conflict?
Well, not even if. It's a comment. I think
Oh.
there always is domain knowledge.
Oh, okay.
It's like, in a way, like, I kind of wish there was a data store that would help me as the domain engineer to say, oh, like if I could start a transaction and say, here's what I'm trying to do, and I want you to just record this. So there's a failure, you know, to call, there's a merge failure. You're going to call
Right.
with these parameters to tell me what I was trying to do.
Right, okay, so his observation was he would really like a database where he could kind of load in some kind of stored procedure about how to execute the operation so that the system could take care of the retries transparently. That would be interesting, yeah. Other questions? Yes?
It occurs to me, and tell me if I'm wrong, and maybe you tell me if I'm wrong, is the question, is right skew possible? Is that the same question as, can two different operations on different machines both produce the same Lampard time value? Is that an equivalent question?
Okay, so yes, two separate batch writes could end up with the same write timestamp.
You wouldn't,
Would not know.
you wouldn't put like a machine ID at the end of the timestamp to make it?
So if the user wants, they can keep a separate table that is the transaction log. And then that transaction log, they would see two transaction IDs with the same write timestamp. And if they store enough information about what the transaction was, they can trace it back to which rows were involved in each one. So you could do something like that to separate out rows with the same timestamp that potentially came from different transactions. You could do something like that to separate out which rows belong to which one.
Seems like you can put the machine ID in the low bits of the clock value, and then, I mean, one would win.
Uh-huh.
It would be random who
Uh-huh.
won, but one of them would.
That's an interesting, yeah, okay, cool. Does that address what you were asking about right skew?
I would have to think more about it, but just your reply that this unfortunate situation can occur in the current design, and the application programmer on top of writing code on top of Treode has to jump through various hoops to detect it and possibly remedy it. It doesn't sound ergonomic to me.
Okay.
I don't want to write that code.
All right, okay, so the comment was it doesn't sound very ergonomic to have to try and separate out different rows from simultaneous transactions. Yes?
Other than Treode, what do you think are the most interesting persistent stores out there?
You know, I kind of like Redis. It has a very simple interface, and it has a multi-write that gives you transactional capability. Its only limitation is it's limited to a single node. But otherwise, as a database, I find it very nice to use. Yes?
So in discussions involving eventual consistency, that characteristic, eventual consistency, pertains to the order in which readers can observe changes to a single key value pair.
Okay, right?
The reason why I find discussions like that frustrating is because the interesting question for many applications is, in what order do changes to different key value pairs become visible to readers?
Okay.
Right? Sometimes it's really important for the application to ensure that when it makes changes to key A and key B, clients cannot see the changes in the opposite order. Right? In Treode, is it possible to arrange guarantees of that form?
Okay, so the question was, if the client writes key A and then later writes key B, are we guaranteed that key B has a greater timestamp?
Or that it's not possible for any observer to see the changes in the opposite order?
Right, once the rows are written with the timestamp, that's it, that's their timestamp. I'm not clear if you're thinking about two different writers writing A and B, or if it's one writer.
Let's for starters, let's talk about a single writer modifying key A, modifying key B.
Right.
And he wants a guarantee that readers cannot see the modifications in the opposite order.
Right, okay, so the writer can arrange for that when it's one process that can, or even when it's different processes. As long as one writer can in some way notify another writer of the timestamp that the first writer got, the second writer can use, can arrange that the next timestamp will be higher.
Databases that are merely eventually consistent provide no guarantee even when the writer is only a single element.
Okay.
A single writer, single reader. The writer writes A, then writes B. The reader sees the modification to B before the modification to A. Sometimes that makes it impossible to write applications.
Okay, I see.
If I could just follow up on that, I'm not sure I understood the answer. You're saying you can guarantee that key B would have a later timestamp than key A, but the question was, can any reader see them in the repository? Is that the same thing or not?
Right. So the writers can guarantee that the timestamp increases. The readers will see the timestamp that it's written with. They aren't going to see some other timestamp. The timestamps don't change once they're written.
Right, but you could see a newer key before, without knowing that all the key has been changed.
Okay, so if a reader comes in and sees the new key, subsequent writers are going to be forced to use a timestamp greater than that reader had used to see the original key. The crowd's getting restless now, so we'll let you go, but thank you very much for your time.